find internal forces just to the left of C, or as I designate it, C minus. Create a free body diagram. If we picture the cut we will have to make here through point C, or just to the left of point C, we'll have our choice of everything to the left of it or everything to the right of it. But if we look at either of those pictures, everything to the left will include this collar at D. Everything to the right will have the roller, or I'm sorry, the rocker at B. So either picture we would draw and we will draw for the internal structure will have an external force or a reaction force involved there. So the first step we want to do is solve those external reactions. All right, so if I simplify this beam that I'm isolating, I have the collar and then the beam, and then I'm taking away the rocker portion of it. So the blue kind of pipe structure is my picture. I'll start here by looking at the external reactions while I'm at it. So at D, where the collar is connected to that pipe, it's outside that pipe, I'll have reactions there. And where I remove the rocker, I will also have reactions. So let's start at B. What is the reaction or reactions at B going to look like? Right, so the rocker allows a little bit of motion along the direction of the surface, but it's going to act basically the same as a roller, at least for small amounts of motion. So it's going to prevent motion orthogonal to that surface. So I'll have some force pushing that I'll call B. That's going to be 30 degrees from the vertical axis. Right, so that covers B, and the rocker allows rotation around the Z-axis coming at us, so there's not going to be a moment at point B. Coming over to the collar at point D, we'll start with a dx. So because the collar is around that pipe, I can't move this left or right, so there's going to be a dx that I'm going to assume is pointing to the right, but it could actually point to the left. Translation-wise, it can move up and down along that pipe, though. It does not prevent that motion. And it does say it's a smooth collar, so we're not going to be worrying about any friction effects there. So there's not a y component of this force. So a dx but not a dy only prevents motion along the x direction. And then moment-wise, if we try to rotate around the z-axis at that collar at D, we can't do it there because it's going to bang into the top and bottom of the collar on that pipe there. So any rotation around the z-axis is prevented. Now around the y-axis it is allowed, but in 2D we're only concerned about rotations around z. So there'll be some couple there, I'll call m sub d, and I'll assume it's in the counterclockwise direction. Well, but this is what the pipe is doing to the collar. Okay. So the collar can't rotate this way, nor can it rotate that way. Yeah, we're not at the internal yet. Yep, so externally, I'm making this assumption. It could turn out to be the other direction, and this would prevent rotation clockwise or counterclockwise. We have three unknowns from that. We have one distributed load, a triangularly distributed load, and we have a point load. I'll just copy the point load down here of 60 pounds. And in my external picture, I can simplify the distributed load into point loads acting at the correct locations. In this case, I have, if I look at the whole triangle, DB, and then the apex of 15 pounds per foot, I could treat this as some scalene triangle. I could find its area. I could try to find its centroid. I would say it's probably easier, at least at this step, is instead of treating it as a single triangle, I'm just going to treat it as two right triangles. So I'm not going to simplify it into a single point load. I'll simplify everything from A to C as one triangle and find its equivalent value and its equivalent location. And I'll treat CB as its own triangle, and I'll get a second point load there. So I will get two point loads, one for each triangle here instead of one. It's not going to it'll make my equations just a little bit more to deal with, but it's not going to be that bad. So I'd recommend doing it that way. Just treat it as right triangles. They're just going to be easier to calculate their areas and so forth. So if I look at the triangular part that goes from D to C, that right triangle has a base of 3 feet. It has a height of 15 pounds per foot. So the area it's going to have is 1/2 times 3 times 15. So for my left triangle, that's going to be 22.5 pounds. Again, this is only the right triangle with the base from A to C. And I know for a right triangle that its equivalent, its centroid is located 1/3 of its base from where the right angle is. So the right angle is at C, which means that the centroid of it, or where this point load is acting, is 1 foot from C and 2 feet from D. Then separately, I'll look at the triangle with its base from C to B. So that has a base of 1.5 feet times its height is also 15 pounds per foot, and divide that by 2. I get about 11.3 pounds. And 1/3 of its base is 0.5, which means it's 1 foot to the left of point B. With our complete free body diagram, we can find the external reactions for this problem. I'll start in the y direction because I know I'll only have one unknown. I'll have B. So in the y direction, I have 3 point loads all facing down. I have negative 22.5 minus the 60 minus 11.3 plus B cosine 30. So what value do you get for B? So we should get that B is positive 108 pounds. Solving, now that we know B, we could go, really the order we do it in doesn't matter from here. Sum of forces x will give us the value for dx. Dx only points to the right. And now I'll have minus B sine 30. So what do we get for the value of D? Right, 54.2 pounds. And that does point to the right. And I took the moments around B in my picture. Looked a little bit easier. I did that just so I could avoid having to use B here, since it will just reduce all the things I have to compute. So if I take the moments around B, I'll have M sub D, that couple, plus the 11.3 times 1, the moment caused by the simplified point load of the right triangle, plus 1.5 times 60, plus the 22.5, and its distance is going to be 2.5 away. And this is equal to 0, so MD should have what value? So this encompasses kind of the chapter 5 and distributed load, well, part of the distributed load part of this problem. Going inside, so I can analyze the forces acting at just to the left of point C. I can make this cut, take everything to the right, take everything to the left. Really based on what's going on up here, I'm going to make my cut and I'll use everything to the right. Looks like there'll be just less to work with. So I'll make the cut through just to the left of C. And include everything that's acting on my beam just to the left of point C. Point B, I have this force, and I know its angle is 30 degrees. And I found from the previous section that it has a value of 108 pounds. And also point B, we're going to assume is connected through the centroid of the beam. Because I'm cutting just to the left of point C, then this picture will include the point load of 60 pounds. Right, so the only difference between C minus and C plus would be in C minus I include the 60, in C plus I would not include the 60. But other than that, everything would look the same. Now I have to include for the piece I kept, I have to resolve only the amount of the distributed load that touches from C to B. So I only have to worry about this part of the triangularly distributed load and simplify that on this beam. So actually, I did do that work already. So I'll have that 11.3, 1 foot from the left, 0.5 feet from the left, and 1 foot from the right. This part of the beam doesn't know that the other half of that triangle is there. If I had chosen to take everything to the left of my cut, then I would have to simplify this part of the triangle would be in that left side of the picture. But this side of the picture doesn't know it's there. All right, so I have the point load, the simplification of the distributed load just that touches CB. B is included. I'm assuming it's through the centroid. And then where I cut it, where I separated it just to the left of C, I can now see the internal normal force P. And note, in the homework, they've been calling the internal normal force N. They mean the same thing. P and N are equivalent. But I will always be using P to designate internal normal force. I will also have the shear force, I'm assuming up. And the internal bending moment MC, I'm going to assume clockwise since I'm cutting on the left edge of this piece here. So my assumptions are on a left cut that V is up and MC is clockwise. If I kept the other side, I would have made the assumption VC was down and that MC was counterclockwise. All right, so in my internal cut, I've introduced 3 new unknowns. Which I can now solve for. In the x direction, I will have PC to the left, so negative PC, minus the 108 sine 30. So I should be finding that PC is negative 54.2 pounds. That internal normal force, because it's negative, that's going to say that I'm in compression. In the y, I'll have negative 60 because I include that, that point load. Minus 11.3 plus 108 cosine 30 plus VC, assuming it's up. So my internal shear force, negative 22.5 pounds. Finally, taking the moment around that centroid of my cut, point C, I'll have a negative M sub C since I assumed it was clockwise. The 60 pounds passes through point C, P passes through point C, VC passes through point C. I'll have a minus 11.3 times 0.5 from the distributed load, plus 108 cosine 30. And that vertical piece of the 108 is acting 1.5 feet away from C. And we were told to assume that B was acting at the centroid, so the horizontal piece of B is also going to have its line of action pass through C, so it will not be, the horizontal piece will not be included in my moment equation.